Hello everyone, again welcome to the latest lecture session. So we have been discussing the aspects relevant to what is it now, the surfactant extraction, I guess, right? And we looked at some of the theory, and let's take that through and solve a particular problem in this regard, right? But again, a quick recap of what we have been up to, right? So we typically add surfactants, let's say, right? And how do they help us? As in one, let's say if you have colloids of NaPl, right, and now by addition of surfactant you are going to help stabilize them, let's say, or help bring them together, either particles or colloids of NaPl. Addition of this surfactant will help stabilize them. This is the NaPl, and here are your surfactants. And surfactants, what is the key here? Here you have a hydrophilic head and hydrophobic tail, right? So obviously NaPl, which is more hydrophobic, right, and you are going to have the tail thus having affinity towards this NaPl, and that is what you observe here. And then let us say it will also help mobilize the NaPl flow or facilitate NaPl flow. As we looked at the case, let us say when we have two soil particles and you have a blob of NaPl and you want to squeeze this through this particular pore space, let us say, right. But this will have high interfacial energy, let us say, right, or high considerable so that is relatively difficult to squeeze this through. So addition of this particular surfactant, let us say, will help in what do we say, forming a surface, right. Again, without this formation of surface, you are going to have to require a lot of energy to squeeze this through, right. So again, to get through that, let us say, or go around that, you are going to add the relevant surfactant, which will help in formation of surface and thus help in mobilizing the NaPl, let us say, right. So that is one aspect. And the third aspect which we looked at, right, what was that about? That is the case where it is not the physical characteristics per se, right, but that let us say after I add enough of the relevant surfactant. So initially all the surfactant that I add will be in the dissolved phase, right. So this is the dissolved phase, and obviously you see after a certain threshold the concentration in the dissolved phase is constant. So what happens to the surfactant that you add after you reach this particular threshold, which we are referring to as the critical micelle concentration? Obviously we are going to have formation of the micelles, let us say, right. And what is the key aspect here? That once all the interfaces are occupied, you are going to have the surfactants form micelles, and they orient themselves in this manner, right. And these particular micelles act again as what do we say, reservoirs for absorbing, let us say, the relevant NaPl, let us say, or the relevant hydrophobic contaminant, right. So what happens out here? We have, let us say, total mass m at time equals 0 initially is based on mass in the aqueous phase or dissolved in the water, or mass adsorbed onto the soil plus mass in the NaPl form, right. So after addition of, let us say, maybe enough surfactant, what is going to happen, or if there is addition of surfactant, what is going to happen? So I am going to have mass of the contaminant in the surfactant, right, and because the total is the constant, what is going to happen? The mass of the contaminant in the soil is going to be transferred to mass in the surfactant, and also mass of the NaPl, let us say, is going to be NaPl is going to dissolve and the contaminant is going to change phase, and let us say is going to be adsorbed into the micelle, right. So again, keep in mind that the total mass is constant, but that we are just changing the contaminant from one phase to the other, as in from soil and the NaPl into the micelle, right. So that is what you observe here. So if you add enough surfactant, what is going to happen? You are going to see to it that your relevant NaPl might completely dissolve depending on how much you add, right. And also you are going to see that, let us say, most of the relevant contaminant from your soil is going to be desorbed, let us say, right. So that is something to keep in mind, and in that context we are going to have the retardation factor. Without the surfactant, what will the retardation factor will be? It will be m time equals 0, or total mass by mass in the aqueous phase, but with the surfactant the retardation factor will be equal to mass or total mass by mass in the aqueous phase and mass in the micelle phase, right. So as you see, R dash is decreasing now, right. And why is this relevant now? Let us say, as we looked at in previous case or multiple examples, let us say we see that either the observed rate constants, let us say, or more importantly the rate at which you will be able to pump out your particular what do we say, solution, let us say, which here includes both the surfactant and the water, right, will be affected by the retardation factor or the amount that is, let us say, adsorbed onto the soil or present as NaPl. So, here by decreasing the R dash, or by increasing the concentration of the compound in the surfactant, what are you doing? You are going to make it easier for you to pump the relevant case out. So, what will it look like, let us say? So, let us say I can have, this is my subsurface and this is my pump out, let us say, right, and let us say this is my water level. So, along with the surfactant and the water and the contaminant will be pumped out, right. So, this is the subsurface, this is the groundwater level, let us say. So, I am going to pump it out, right. So, again what are the key aspects here? Let us just understand that. As in one case is that, as in I am not adding any additional reagents though, right. Right, I am not adding any additional reagents or such, right. But obviously, for this particular system to work, as in this particular case of being able to pump the relevant surfactant and the soil out, obviously the soil needs to be relatively permeable, right. It needs to be relatively permeable. Yes, that is something to keep in mind, otherwise obviously you are going to have issues with pumping the relevant solution out, right. So, another aspect is, after you have pumped out, let us say, all the relevant contaminant and most of the surfactant, you are going to still have the residual surfactant in it, right. So, it is like maybe I guess it is a very generic example. Let us say you are trying to wash the grease off your shirt, let us say, and you apply a lot of detergent or surf, let us say, right. And what is going to happen? You are going to obviously have what do we say, if you add very high levels of the detergent, you are going to observe that the residual what do we say, surf will be, what do we say, affecting the cloth quality or such, let us say, right. So, similarly, let us say if you add a lot of surfactant, obviously even after you pump out most of the surfactant, you will have some or residual surfactant. So, that is some aspect to keep in mind, as in does that introduce any other complications, or typically let us say any other toxicity or such effects, right. That is something to keep in mind, right, as in residual surfactant and your ability to even remove that particular residual surfactant needs to be kept in mind, right. So, these are the aspects obviously we will look at. So, typically we are, when we are pumping it out, let us say, let us just look at the simple mass balance. What is it going to be like? It's, if it is just pumping it out, let us say, as we know, it is going to be equal to dC by dt, right. If I take the advection term on to the right hand side, it is going to be minus u dC by dx, right. But this needs to be affected by the retardation factor, right. So, now instead of R, I have R dash, right. So, as you can see now, let us say, right, R dash, let us say, is smaller than R, and you see that the efficiency with which, let us say, you can pump your relevant contaminant out obviously increases, right. So, that is something to keep in mind. So, one aspect is this, let us say. So, again, how do you typically wash the soil, let us say, either in situ, right, or ex-situ, as in you pump the, not pump, excavate the soil, take it out to a particular location and relatively wash it there, let us say. So, you can get it done ex-situ, and typically quite a few operations look at ex-situ too, I mean ex-situ cases. And because, why is that? Because of what do we say, either ease of use, let us say, and ease of application, or because of site characteristics that would prevent in situ what do we say, application of surfactant and pumping the surfactant out, right. So, in this case ex-situ, as in I am removing all the soil, taking it somewhere else and then trying to treat it. So, in this case, what is the best way to be able to maximize or increase the efficiency of your particular operation, right. The key is that you have contaminated soil, let us say, at concentration C naught, let us say, right, and you have surfactant, let us say, right. So, what is the best way to go about it? Is it just that you mix everything, as in all the soil, all the surfactant, and then remove the surfactant, or how best to go about it? As you can see, let us say here we are concerned about desorbing the contaminant, right, from the soil into the surfactant, right. So, let us say if I can say something like this, and if this is my soil particle and this is my contaminant, let us say, and then I introduce, let us say, surfactant, let us say this all this volume is my surfactant. So, after equilibrium is reached, what will happen? Let us say this is the initial case when most of it was on the adsorbed on soil, right, and let us say after equilibrium has been reached, let us say I will have most of it in the surfactant now, right. But as you can see, this is the case, or this is what I have here, right. So, what does it depend upon? Again, there is going to be an equilibrium between the contaminant adsorbed on soil and the contaminant concentration in the micelle or in the surfactant, pardon me, right. So, there is obviously, when will you maximize your efficiency, right. So, when the gradient, or when the concentration difference between that in the surfactant and your soil is greater, right. So, to achieve that, what do we typically look at? Rather than mixing everything, let us say, in one go, right, and then again having slightly contaminated soil for which again you need to add fresh surfactant or such, what do? We look at an approach called the counter current, let us say, counter current flow, right. As an if this is my relevant system, right, I introduce the dirty soil here, or the contaminated soil, let us say, dirty soil here, and this goes out this way, right, and here I end up with the clean soil, right. But here obviously I need to have surfactant, and how do I introduce that? If I introduce the clean surfactant here, right, what is going to be the case? Obviously the what do we say, you are going to have desorption here, but the issue is here that as it passes through, let us say, your slightly contaminated soil will be in contact with the surfactant that already has the relevant contaminant in it. But to achieve pretty good clean soil, let us say, what would you do? You would see to it that your cleanest soil, let us say, would come in contact with relatively clean surfactant, let us say, right. So, even if there is, let us say, minor concentration of contaminant adsorbed onto the relevant soil, right, that will be desorbed because the surfactant is relatively clean. So, as it passes through, and this is why we call that counter current, right, we end up with the relatively dirty surfactant here, right. Typically we see that this, so the dirty soil comes in, clean soil goes out, and in the counter current we add the clean surfactant which comes in contact with the relatively cleaner soil, and while it goes out it is relatively dirty, but again it comes in contact with the relatively more dirty soil, right. So, this is what we typically look at, the semi continuous counter flow, right. But what is the aspect here, or what is the issue that we face here, right? It is that, let us say, right, soil is not easy to is not malleable enough, let us say, right, or if I am looking for a better term, the ease with which you can handle soil or put up in such a system is going to be difficult, let us say, right, it is not easy, right. So, how do I achieve this counter current flow? So, I make that semi continuous, let us say, semi continuous counter current flow, right. So, how do I have that? Let us say, so I have a series of containers, let us say. So, I have my soil here, let us say, dirty soil and so on and so forth, right. So, what is going to happen? Let us say, now the contaminant, let us say, is in this direction, let us say, or you can keep the contaminant in the same container, right, and you will have the surfactant flowing through in this way. And this is what is done typically though, right. So, the surfactant, right, and the soil comes out. So, what do we typically do now? We have a series of bins, right. Either you change the soil from one bin to the other or just keep the bins moving, but what is the aspect here? That the cleanest surfactant, here we introduce the cleaner or cleanest surfactant comes in contact with the relatively cleaner soil now, let us say, right. So, again here you are going to have relatively more removal of the relevant what do we say contaminant from the soil, rather than if you had relatively dirty surfactant in contact with the relevant soil, right. So, that is what you have here. You want to increase the what do we say extent to which you are going to be able to decontaminate the soil. So, that is why you have the clean surfactant coming in, and that will come in contact with the relatively cleaner soil. So, this particular cleaner batch of soil will be removed, right, and will be replaced by the next in line relatively dirtier, let us say, a batch of soil, and again that is going to come in contact with the fresh batch of the clean surfactant. So, what happens to this surfactant though, as it keeps passing from one bin of what do we say, contaminated soil to the other, right, and here you are going to have the relatively dirty or contaminated surfactant, right, and this you are going to dispose out there, right. So, obviously you know you are going to have fresh batch of contaminated soil coming in, and what do we say, simultaneously let us say a batch of clean soil or decontaminated soil leaving, right. At the same case you will have what we say, the surfactant coming in and the dirty surfactant being removed, right. So, that is how we typically go about it, right. So, now let us move on to maybe looking at a particular minor example, let us say, before we move on to let us say looking at a particular case study or such, right. So, I believe I have an example here, let us look at that. So, let us try to understand the system here. So, here we have a source zone and looks like that is 200-meter long, okay, 50-meter wide and 10 meters deep, yes, and it has bulk density, the soil bulk density is given, right, and the fraction of organic matter is also given, FOC. And why is this important now again? Because as we know, let us say it is the, when we say soil absorbs the contaminant, it is actually the organic content in the relevant soil, right. So, that is something to keep in mind, right. So, FOC is relevant here, right, and porosity of 0.4, porosity of 0.4, this we obviously assume that it is occupied by water. So, it is contaminated with what do we say, trichloro or maybe is it tetrachloro, I will take it as tetrachloroethylene, let us say TCE here with an average aqueous concentration of 15 milligram per liter. So, it is the average aqueous concentration is 15 milligram per liter of this chlorinated solvent, which is a toxic compound TCE, this is in the water now, right. And pure NaPl is present in 1% of this pore space, as in S, the fraction of the pore space occupied by the NaPl is 1%. Again we are saying that the NaPl is pure, right. So, when I say NaPl is pure, so what does that mean? X NaPl, the mass fraction of that particular or mole fraction, pardon me, of the NaPl is equal to 1, let us say, right. So, that these are the aspects we have until now, and it is to be extracted with a surfactant that has a CMC. What is CMC? It is obviously the critical micelle concentration, and we obviously need to add enough surfactant, you know, such that we are, you know, we cross this limit of CMC to be able to fall in the micelles, let us say, has a CMC of 200 milligram per liter, right. So, as in S total is equal to S dissolved, let us say, plus S in the micelle phase, right. Again this for this particular dissolved phase, for this particular micelles to be formed, obviously you need to first reach the CMC here, right. CMC let us say is around 200 milligram per liter, let us say, right. And the empirical relationship between the partitioning, what we say, that to describe the partitioning to micelles formed by this surfactant, let us say, is given here, as in, as we understood earlier, the mass fraction of the contaminant in the micelle is going to be depend upon the mass fraction of the contaminant in the water. This is the mass fraction. What is this? Mass of contaminant per mass of micelle, let us say, or mass of surfactant in the micelle phase, that is Y, right, and this is mass of contaminant per mass of water, let us say, right, and that is the relationship is depend upon the micelle water partitioning coefficient. I guess it is self explanatory. Again we looked at octanol water partitioning coefficient. So, again rather than measuring micelle water partitioning coefficient, we come up, we have this empirical relationship that gives us an idea about how KMW is dependent upon KOW, and that is what we are going to use here, right, to be able to come up with this KMW, right. It is difficult to obviously measure that directly. So, here we have three aspects to look at, and let us look at what they are, right. So, we have that we need to calculate the minimum total surfactant concentration that we need to completely dissolve the NaPl, right. So, we are going to have to come up with this concentration which will what we say lead to it that all this NaPl 1% NaPl let us say is completely going to dissolve, let us say, if the extractant solution were added to the soil at a volumetric ratio of 5, as in volume of surfactant solution to total volume of soil. So again obviously the aspect is that we add a lot of surfactant, right, as we keep adding and looking at it. So we are looking at the total what we say equilibrium case, let us say, right, or the holistic equilibrium case. So the key aspect is that if the extractant solution were added to the soil at a ratio of 5, which is the case with respect to surfactant solution to total volume of soil. So that is one aspect. We will look at how to solve this, and what would be the equilibrium concentration in the aqueous phase and the total concentration aqueous phase plus micelle phase of the extracting solution if the same surfactant concentration calculated from this particular case were added at volumetric ratio of 3 instead of 5, right. So as in let us say earlier we are, or in case A we are adding, or we plan to add what we say a certain volume of surfactant, but in case B let us say we are adding a relatively lesser volume of surfactant, let us say, and we want to achieve the same results, and then we are obviously asked to calculate let us say the concentration let us say in the solution, which means concentration in both the water and the micelle phase, right. And then the same case with respect to now, as in repeat the calculations of part B at a volumetric ratio of 7, let us say, as in initially we looked at a case when we are adding the volume of surfactant at ratio of 5 compared to the volume of the soil. Then we are looking at a case as in what will happen if we add lesser amount of surfactant and also obviously more amount of surfactant, right. So let us look at case A first and then take it through from there, right. So let us look at case A. What do we have here now? We have, what is the approach here? Total mass we can calculate, right, based on the mass of the relevant contaminant in the dissolved phase plus mass of contaminant adsorbed onto soil plus mass of the contaminant in this particular NaPl, let us see, right. So this is how we will calculate the initial or total mass, let us see, and this total mass obviously is going to be constant or the same even after you add the surfactant, right, as in that you are going to have a change in the relevant concentrations and so on. But here we do not have enough data, or some data is not available. So we need to be able to make some assumption, as in let us say we know that this is nothing but epsilon V C naught, right, plus V rho B into Q. So this will be 1 minus S, but we will, so this is V into or S epsilon V into X NaPl, this is 1, so I will skip that, and density of NaPl, let us see, right. So here is the density of NaPl given, well it is not given, right, this NaPl is TCE. So this density of TCE can be found out from the relevant literature, that we can find out, right. So we do have density of what do we say, the relevant soil though, right. So we do have density of soil, we have C naught, I think we have partitioning coefficient here somewhere, yes, and if not we can get that particular case too. Even if we do not have partitioning coefficient we can get that, right, for this particular TCE we can get that from the relevant literature too, right. Again from that I can calculate Q, I have C naught and so on. But what happens to this system once I add surfactant though, right? You are going to see a decrease in C, decrease in C naught, and we are going to look at complete dissolution of this NaPl, let us say, right. But here as in we do not know what the concentration is going to be in the water after let us say dissolution of this NaPl or addition of surfactant, right. So to be able to get around that, we are going to make a conservative estimate. The conservative estimate is that we are going to estimate that even after addition of surfactant that this concentration C dash will almost be equal to C naught, but this is not a great assumption, but this is a conservative what we say estimate or assumption that we are making here, right. So that is fine for now, right. So what is the approach here? We are going to assume that this C naught is going to stay the same even after addition of surfactant, but as you know that is not going to be the case, right. But after addition of surfactant, how is this going to transform into? It is going to be the total mass will be equal to the one in the dissolved phase plus one in the soil plus the one in the surfactant, right. So we know that this we can calculate from this particular set of variables, and we are going to then substitute out here and calculate the relevant variable here. What is the minimum total surfactant concentration, right. So that is something that we are going to calculate. So let us see, let us have the relevant approach here. So mass of TCE in the contaminated source, as we know, as I mentioned earlier, this is the one in the dissolved phase, right, and this is the one in adsorbed onto the soil, and this is the one in the relevant NaPl, let us see, right. So this is what we have right now, or the initial case, and the total volume, this is the total volume, and we are calculating that total volume as 1 into 10 power 5 meter cube, right. This is from 200 into 15 to 10, that is given in the question. So, we have that particular case, let us say, right. So, let us move on. So, we have the mass fraction, or not mass fraction, pardon me, the pore fraction, let us say, that is occupied by NaPl, that was at 1%, right. So, that is why this S is equal to 0.01, and porosity we also have that at 0.4. So, Kp is equal to FOC into KOC, and again FOC was given. FOC is nothing but the fraction of the organic content, I guess, right, and KOC again, this is from a literature value, let us say, for this particular case of TCE, right. So, again what is this? This is the partitioning coefficient, which is going to be dependent upon the amount of organic content in the soil, and also the partitioning coefficient between organic carbon and the relevant what do we say, water for that particular contaminant, let us say, right. So, that is what we have here, and this I guess was 0.5%, that is what we have here, and looks like the partitioning coefficient is something like 0.63 ml of the TCE, let us say. Is it of TCE? No, yes, I guess so, because the units are going to be in such a case, right, per gram, let us say, right. So, that is something to keep in mind. The units are something to keep in mind here, and you will be able to understand the units, let us say, once you look at these, the units of this particular KOC here, let us say, right. So, we have the partitioning coefficient here. So, from that what can I calculate? Again I have the density of NaPl given, and this mole fraction of NaPl, again pure NaPl, right. Mole fraction is nothing but what do you say, moles of that particular NaPl, let us say, or that particular contaminant, let us say, by the total number of moles, right. But as we know, let us say, it is pure what do we say, NaPl. So, both you do not have anything else other than that particular contaminant, let us say, right. So, this is going to be equal to 1, and that is what we see here. And moving on, let us say, so this mass is nothing but 1 minus S into porosity times volume times concentration of the relevant contaminant in the water, right. So, this is nothing but the volume of the contaminant that is dissolved in the relevant water here, right. So, let us look at the other case. So, here we have V, right, and I think this is the bulk density, and this is your V, rho B and Q, is it, I guess, right. So, it is V rho B times Q, right, that is what we should supposed to have, yes, and this is nothing but the contaminant concentration in the relevant soil. So, this is what we have out here, and this maybe needs to be multiplied by 15, maybe I am missing that particular value, as in we know that the mass in the relevant soil is going to be equal to V rho B into Q, right, and that is going to be equal to nothing but volume times rho B into Kp into C, right. So, we have these three variables here, right. So, this has to be multiplied by that 15 gram per, or this particular concentration of the relevant contaminant in the relevant soil, let us say, right. That is what we have here. Okay. So, and this is nothing but the concentration of contaminant in the NaPl. So, let us look at what we have. This is S times porosity times volume and density of NaPl, mole fraction of NaPl, right, and that is what we have. This is just changing in the units. So, this is the mass in the soil, in the water, mass in the soil, and mass in the NaPl, right. So, let us just look at those values here. As you see, we have 5.95 into 10 power 5, order of 10 power 5, let us say. This is order of 10 power 6, and this is order of 10 power 8, let us see, and total we end up with these many grams. We will come back to that, but the reason I write it out in this way is that, let us say, compared to the amount, if I look at the fraction, what is it now? 1 is to 10 is to, let us say, 1000, right. So, if one part of the contaminant is dissolved in the relevant what do we say, water, you have 10 parts adsorbed onto the soil and 1000 parts present as the NaPl. Again, NaPl was only present as 1% of that particular pore space, right. So, you should understand the relevant what do we say, criticality of having or complexity of having NaPl present in your particular what do we say, contaminated site, let us say, right. So, end up with almost, let us say, 5.88 into 10 power 5 kg now, right. So, you can understand the mass of the contaminant that we are talking about in just this 200 into 50 into 10 space of the relevant contaminated soil, right. So, I guess I am out of time. So, we will continue this in the next class. Again, what is the approach here? We now have this particular mass of contaminant, we will just equate that to the case when, let us say, we have no NaPl, but just the surfactant, right. So, I guess with that I will end the session for today, and thank you.